Good day everyone. Today we will explore colligative properties of solutions. These are properties that change when a solute is added to a solvent. Our focus will be on understanding these properties, the effect of concentration, the difference between non-electrolyte and electrolyte solutions, and solving problems to calculate boiling point elevation and freezing point depression.
Now, let's talk about the introduction of colligative properties. First, what are colligative properties? These are properties of solutions that depends solely on the number of solute particles present, not their chemical identity. The four main colligative properties are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. These properties change because solute particles disrupt the natural behavior of the solvent molecules. Then, why do electrolytes have a greater effect than non-electrolytes? Because electrolytes ionize in solution, producing more particles, while non-electrolytes do not ionize and contribute fewer particles. Now let's move on to
Effect of concentration on colligative properties. Now let's talk about how concentration affects colligative properties. The greater the concentration of solute particles in a solution, the stronger the effect on lowering vapor pressure, raising the boiling point, and lowering the freezing point. For example, a solution with 2 moles of solute in 1 kilogram of solvent will have greater boiling point elevation and freezing point depression than a solution with only 1 mole of solute. Why does higher concentration increase these effects? More solute particles disrupt the solvent natural behavior, causing more significant changes to its physical properties. Non-electrolyte versus electrolyte solutions. Now let's differentiate the colligative properties of non-electrolyte and electrolyte solutions.
non-electrolytes do not ionize in solution, so the number of solute particles equals to the number of moles dissolved.
Electrolytes, on the other hand, ionize and produce multiple particles per formula unit. For example, sodium chloride dissociates into sodium cation and chlorine ions, effectively doubling the number of particles in a solution.
Now, since we know what is colligative properties and what is the effect of concentration on colligative properties, and we also discussed the difference between non-electrolyte and electrolyte solutions, now let's move on to solving problems to calculate boiling point elevation and freezing point depression. First is boiling point elevation. The boiling point is the temperature at which the vapor pressure of liquid is equal to the atmospheric pressure. It is happened when a solute is added, the boiling point of the solution increases because the vapor pressure of the solution is lower. The molar boiling point constants for some substances are given in the data table, which is for solvent is the acetic acid, which is 3.22 degrees Celsius per molality and 118.1 degrees Celsius for normal boiling point. For benzene is 2.64 degrees Celsius per molality and 80.2 degrees Celsius for normal boiling point. For carbon tetrachloride, 5.02 degrees Celsius per molality and 76.7 degrees Celsius for normal boiling point. For chloroform is 3.63 degrees Celsius per molality and 61.2 normal boiling point. For ethanol, there is 1.23 degrees Celsius per molality and 78.4 degrees Celsius for normal boiling point. And the last one is the water. There is 0.512 degrees Celsius per molality and 100 degrees Celsius for normal boiling point. The relationship is given by delta T sub B is equal to K sub B multiplied by M, where delta T sub B is the boiling point elevation, K sub B is the boiling point elevation constant, and M is the molality of the solution. This is an example problem. Calculate the boiling point elevation for a solution containing 3.5 grams of sugar. Molar mass is equal to 342 grams per mole dissolved in 150 grams of water. Case sub B for water is 0.512 degrees Celsius per molality. These are the given. First is solute, which is sugar, C12H22O11. Mass of solute is equal to 3.5 grams. Molar mass of solute is 342 grams per mole. Mass of solvent is 150 grams or 0.150 when we convert into kilograms. Boiling point elevation constant or K sub B is equal to 0.512 degrees Celsius per molality. First is we're going to solve for the molality by the given formula, which is M is equal to moles of solute is divided by kilograms of solvent. But first, we're going to find the moles of sugar. So 3.5 grams of sugar times 1 mole is divided by the 342 grams, which is 342 grams is the molar mass of sugar. Since we will going to find the mole, let's put it in the numerator, so it gives us answer 0.01023 mole of sugar. By the way, you can also have 2 decimal point if you want. Then next we're going to convert the 150 grams of water into kilograms. So 150 grams of water times 1000 kilograms over 1 grams. So it gives us 0.150 kilograms of water. Then now, we're going to find the molality from the given formula of moles of solute over the kilograms of solvent. So 0.0103 mole of sugar is divided by into 0.150 kilograms of water. So it gives us answer 0.0682 mole per kilogram. So step 2 is we're going to solve for the boiling point elevation. From the given formula, delta T sub B is equal to K sub B multiplied by M. So let's going to substitute. So 0.512 degrees Celsius divided by 1 molality times 0.068 molality. It gives us answer 0.035 degrees Celsius. The last will be we're going to solve for the boiling point of the solution. Since boiling point of solution is equal to the boiling point of solvent plus delta T sub B, we're going to substitute that one, which is 100 degrees Celsius plus 0.035 degrees Celsius. We will have 100.035 degrees Celsius. Now, let's discuss freezing point depression. Freezing point of a substance is the temperature at which the solid and liquid phases coexist and their vapor pressure are the same. Adding a solute lowers the freezing point of the solvent. The table shows a list of some common solvents with their respective molar freezing point constants. For solvent, acetic acid is 3.90 degrees Celsius per molality and 16.6 degrees Celsius for freezing point. For benzene, 5.12 degrees Celsius per molality and 5.51 degrees Celsius for freezing point. The naphthalene is 7 degrees Celsius per molality and 80.2 degrees Celsius for freezing point. The chloroform is 4.68 degrees Celsius per molality and negative 63.5 degrees Celsius for freezing point. And lastly is for water, which is 1.86 degrees Celsius per molality and 1.86 degrees Celsius for freezing point. The relationship is given by delta T sub F is equal to K sub F multiplied by M, where delta T sub F is the freezing point depression, K sub F is the freezing point depression constant, and M is the molality of the solution. This is the example problem. Calculate the freezing point depression for 155 grams of iodine dissolved in 1.2 kilograms of benzene. K sub F for benzene is 5.12 Celsius per molality, and the molar mass of iodine is 254 grams per mole. Here's the given. Solute is the iodine. Mass of solute is 155 grams. Molar mass of solute is 254 grams per mole. Mass of solvent is 1.2 kilograms. Freezing point depression constant, or K sub F, is equal to 5.12 degrees Celsius per molality. And the freezing point of pure benzene is 5.51 degrees Celsius. First is we're going to solve for the molality by the formula given, which is M is equal to moles of solute divided by the kilogram of solvent. So we're going to find the mole first of the iodine. So 150 grams of iodine times 1 mole is divided by 254 grams of iodine. The result is 0.61 mole. So next, we're going to find then the molality, which is 0.61 mole is divided by 1.2 kilograms of benzene, which is the answer is 0.50 mole per kilogram, which is the molality. The next is we're going to solve for the freezing point depression by the formula which is given. Delta T sub F is equal to K sub F multiplied by M. So we're going to substitute that one. So delta T sub F is equal to 5.12 degrees Celsius per molality times 0.509 molality. So it is result of 2.61 degrees Celsius. And then last is we're going to solve for the boiling point of the solution by the formula given, which is T sub F is equal to T sub the pure solvent minus delta T sub F. So we're going to substitute those given. So delta T sub F is equal to 5.51 degrees Celsius minus 2.61 degrees Celsius, and it gives us 2.9 degrees Celsius, and that is the boiling point of the solution. Okay, to sum it up, the colligative properties include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. The effects depend on the number of solute particles and the concentration of the solution. Electrolyte solutions show greater changes because they produce more particles through ionization. So this is the practical example of boiling point elevation or freezing point depression. Like boiling point elevation is used in candy making, and freezing point depression helps the ice roads in winter. So, and that's all. Thank you.